Okay, so I was just taking stock a bit of how much time we have left for the class or the course and the material. So what I think I'll do is I'm not going to cover the rigorous coupled wave analysis because I pretty much I try to restrict that to one lecture period, and that's really not enough to do it justice. So I'd rather cover some of these other topics. I'm going to cover multiplexing and some holographic data storage today, as well as some polarization issue for the approximate coupled wave. And then I'll have the remaining lectures I'd like to spend doing the CGH and the digital holography. So, and we'll have kind of a demonstration lab. There won't be any real assignment for that lab. We'll do that the week after Thanksgiving. Let's see, when is the first week of December? Is that the week after Thanksgiving?
Yep.
Yeah. Okay. So that week too, we're going to have the class presentations, and so what I'll do is, I think for next time I'll come up with a list, an order list for people to give their presentation, so you'll know whether you have it on the Tuesday or the Thursday prior to, at least a week before Thanksgiving. So you can get it ready before Thanksgiving so you don't have to worry about it, and then go from there. Okay, so what I want to cover today, one of the things I want to cover today is the effect of polarization. Now, the approximate coupled wave model, so for this we have our grating, usual case here, and we have our K vector like such, coming off at angle phi, and here's the z direction. And so in the past, what we've assumed really is that we have a TE wave where the field is kind of perpendicular to that to the plane of incidence that we have, and this is the direction, again, rho. Now, but it's possible, and Kogelnik derives this at the end of his paper, it's possible to treat a polarization which is perpendicular to the TE or the TM. So if this is TE or S, as is sometimes referred, this is sometimes referred to as P, polarized light. We can treat these two cases, but it's a kind of a very special case. Polarizations in between cannot be treated. So for that, you need to look at the rigorous coupled wave model, and it's possible to do that. So, all right, so we can treat this and do this. And the way it's done is, when we started our analysis of the coupled wave analysis, remember we had the Helmholtz equation, the scalar Helmholtz equation, del squared E plus k squared E is equal to 0. So this is the scalar Helmholtz or wave equation. Equation for describing the wave propagation. However, the field is really not a scalar. The field is really a vector, and so a more complete form for this wave equation is the following, so where we have del squared E minus the gradient of del dot E. All of these E's are vectors now, plus k squared E equal 0. Okay? And so in the case where, so for the TE case, this term was equal to 0. Okay? And that's how we got away with it. However, for the TM case, as you might expect, it's not equal to 0. Okay? So we get at it by looking at the addition of this other term, this gradient of the divergence, and the field that we assume. Remember, we had started with that, and then we had some assumed field. We still have two fields, right? Only a reconstruction and a signal or diffracted field, E, but now it's a vector. So we have R, and it's a function of Z. This vector is a function of Z. We have the same phase, E to the minus J rho dot R, and then we have plus S of Z, E to the minus J sigma dot R again, where R and S are now, so now we have R of Z is equal to, we have an X component, and we have a Y component, and a Z component in the Z direction. So this is kind of the nature of the vector, and similarly for S, it's kind of the same thing, only with S's in there instead. All right. Now, so this field that we have, again, these are vectors, and we also know something else too, right? We know we have these propagation directions, so we have rho for the reconstruction field, and then we have a signal or diffracted field. This is going to now be, say, the S vector, and this is the E vector. All right, and so the other vectors that we have are that we have, again, rho and sigma are the propagation vectors. All right. Now, this is good to kind of sort of bring together everything that you have, because now we know as well, I mean, for electromagnetic fields, there are transverse electromagnetic fields, right? So when we have a transverse EM field, we know something about the relationship between these vectors, right? We know that if we take the dot product of rho with R, that's equal to the dot product of rho times S, and that's equal to 0, right? Because these are the direction of propagation and the field are perpendicular to one another, okay? And so that cosine of that angle is 0, all right? So now, all right, so now we do the same thing that we did before. We stick our solutions, these field solutions, into that new equation, this new wave equation that we have. And when we do that, we now end up with minus 2j times rho sub z r prime of the vector. And then this is, again, prime in the sense of the z derivative, plus j rho rz prime, not the vector, just the amplitude here. And then we have minus 2j beta r plus 2 kappa beta s equals 0. So there's a vector in each of these terms now. All right, and then similarly, we have a second equation, so we can call this, say, our A equation. And then we have a minus 2j sigma z s prime plus j sigma s z prime plus beta squared minus sigma squared minus 2j alpha beta s plus 2 kappa beta r equals 0, and so we'll call this one a B equation, okay? So, all right, so these are now these are the coupled wave equations that we have for the this more generalized case, all right, where we have, say, a vector for the fields. Now, the those fields, right? So we have r is a vector, but it's also a function of z. And so this vector is equal to an amplitude, r of z, and a times a directional, unit directional vector, a unit vector, r, right? And so we can also write s of z as being equal to s of z times s, another unit vector, right? So these are, again, unit vectors in the direction of the field. Or fields, okay? All right, and so as unit vectors, we know that r dot r is equal to 1 and s dot s is also equal to 1. And from this transverse relationship, now if we substitute that in, we then also have that r dotted with rho, the propagation direction, is equal to 0, and s dotted with sigma that's also equal to 0. All right, so we know we have a couple of kind of relationships which, as you can see here, are zeroing things out nicely or being equal to unit values. All right. Okay, so now, let's utilize that. So let's take the dot product of r. So we're going to take r dot product with that, and we're going to take s and take the dot product with equation b, all right? And so when we do that, we end up with, we now end up with a scalar equation, and we have minus 2j rho sub z r prime, again, the derivative with respect to z, minus 2j alpha beta r, plus 2 kappa beta s. And now, in the end, we have r dotted with s. And that's equal to 0. And for the other equation, for the b equation, we have minus 2j sigma z s prime plus beta squared minus sigma squared minus 2j alpha beta times s plus 2 kappa beta r, again, times this same dot product r dot s equals 0. Okay? And we have the same, we'll use the same kind of notation that we did before, where, if we have that c sub r is equal to rho sub z over beta, and c sub s is equal to sigma sub z over beta, and the tuning parameter is equal to beta squared minus sigma squared over 2 beta. So we insert those functions or those identities or definitions into this pair of equations, and now we have c sub r times r prime plus alpha r equals minus j kappa times r dot s times s, and then we have c sub s times s prime plus alpha plus j times our detuning parameter times s equals minus j kappa r dot s times r. All right, so these now are, our simplified coupled wave equations when we have, you could say this is for non-TE conditions, okay? So what does that tell? What can we say from this then? Well, these equations look identical to what we found before, except that they have this dot product in there, right? And so if we have, for instance, the case where we have the parallel polarization, now we can say simply that we have kappa, say when it's in the plane, is going to be equal to kappa times r dotted with s. All right? Or if we substitute in for this dot product, that's equal to a minus kappa times cosine of 2 times the reconstruction angle minus phi. Okay, in terms of just cosines in for that dot product. All right, so what does that tell us? All right, well, let's so we can take everything we did before and just put in this for this parallel polarization state. All right, so we don't have to go through the whole many lectures of deriving all those cases. We could just apply them directly, all right? And so let's look at just a couple simple cases for illustration, how we might manipulate this to some benefit, all right? So if we look at an unslanted transmission hologram, again, this is a phase hologram, all right? Remember, the efficiency, eta, was equal to sine squared, and we have an argument which was pi times delta n d over lambda cos of theta, all right? And then we have to include in that, so this was like the Bragg angle here, because we're at Bragg for this particular case. So this was what we found before, but now we have this r dot s in there as well. All right? And so let's call all of this, call it C. And so now we can say that we have a situation here where, again, so for the unslanted case, this is going to be, phi is going to be 90 degrees. The k vector is along the x-axis in that system, so 90 degrees with respect to the z-axis. And so we can say that for the TE case, then, we can say that we have sine squared of c, and for the TM case, this is going to be equal to sine squared of c times cosine of 2 theta times the Bragg angle. Okay. All right. So what if we make now c equal to pi over 2? Remember, that was the case for maximum efficiency. Then what we can say is that, so when that's pi over 2, and let's make theta b equal to 45 degrees. Okay, so we have a replay angle of 45 degrees inside the medium. And so when we do that, this Tm term is always 0. Okay, so we can make so that's always 0, and this is always going to be sine squared of pi over 2. Okay, so that's very good. So we're going to have basically we can have a polarizer made from this volume hologram. And so we have a case where, again, we have the TE efficiency is going to oscillate like this as a function of C if you vary C. If you fix it here, you can have a efficiency for your TE is equal to 1, and efficiency for the TM is equal to 0. Okay, so that's a polarizer, right? If you can do that. So if you have you can make polarizers out of dichromated gelatin or the photopolymer material that we use and so forth. Now, the only problem with this particular case is that we have 45-degree angles, okay? And if you think about the refractive index for most of these polymers, and so forth, they're around 1.5. So if you think about that for a second, you realize that you're beyond the critical angle. You have to get beyond the critical angle to get inside the medium in order to make these. All right. So you can do that with a prism coupler. So again, you can come in here at a large angle, larger than the critical angle by doing a index match. Here's your, so you have a fluid there, and then so this is a index matching fluid, and this is your film. So you can actually do this, but it's kind of, and then come in on the other side with another beam coming in at minus 45, and come up and make that unslanted grading with those conditions. However, it's a little bit messy to do that. So let's see if we could do something else to make a polarizer as well. So here, let's now look at this relationship that we have. And so instead of making Tm equal to 0, let's see if we can make Te equal to 0, right? So eta Te will be equal to 0 when C is equal to pi, right? C is basically, again, it's this term here, so that means that all of this is equal to 1. Before it was equal to 1/2, so that means that if, in fact, we can have a material that has a pretty high index modulation range, or linearity of the index modulation, dynamic range of that material, we can get to this other condition where this product or relationship here is equal to 1. All right. So again, so this the Te case is going to be equal to 0, and the if we also have the case where so we have this C now times cosine of 2 theta b for the Bragg condition. If we set that equal to pi over 2, remember this is equal to pi, so we just want this part here equal to 1/2. Then the Tm case, right, the Tm sine squared of C times cos of 2 theta b, that whole part will be equal to 1. All right. So so we can make it. And then the advantage here is that this is equal to 1/2 when theta b is equal to 30. Right. So then we have 2 times that. 60 degrees, that gives us 1/2. So 30 degrees is, we can do that without having to couple in through a prism. All right. So here's kind of a plot. One of my students did this a number of years ago for when we were looking at this. So this shows, what's going on here. So here is the case where, that C is equal to pi over 2, and we reach this minimum or maximum here. In this particular case, since theta, again, in this case is 30, the Tm case, which is indicated by this dashed curve, is not 0 at that point, okay? So it's a lot lower, all right, but it's not 0, all right? But in this case, if we go further in grading strength or modulation, we reach this point here where C is equal to pi, all right? And then in that case, the Te efficiency is down to 0, okay? So, so we have some flexibility in making polarization elements in gratings, all right? So that's very advantageous in a number of situations. So can we do this in actual material? So this kind of shows real-world plot for those same plots that I showed for a dichromated gelatin material here. But it does show that we can make a polarizer out of this material, right? So here's what's going on here. This is our our S-polarized or TE-polarized light. So it peaks up quicker, and when the modulation C, that C is equal to 1/2, and then it drops down, and it goes here almost to 0, and the TM polarization or P polarization increases. This material has enough dynamic range so that will increase, and it reaches a maximum right around where the TE was equal to 0. So we were able to get a pretty decent polarizer out of this with the extinction ratio of 62.7 or whatever. And it's kind of nice because you can make polarizers without spending hundreds of dollars to make a polarizer. Or if for instance, you can do this as well, although we're not going through that here. You can do this as well with surface relief gratings too, because the surface relief grating, again, if you look at that rigorous coupled wave paper by Maharm and Gaylord, they show that when you make a surface relief grating, right? So here's your, say, your surface relief grating. So this might be like a photoresist, and this is air, all right? So what you really have is a index difference. So if you look at slabs of this, and this is the way they do the analysis, so you have slabs of material and no material there. So you can kind of think of this section here as being a volume with a very rarefied low index, which is air, and your higher index here with PR has index like they vary all over the place, but so let's just say 1.5. They go from like 1.4 to 1.7 or something like that. But you can see here that so you have medium, non-medium, but you can treat this still as a volume with air. So you can make this in a photoresist grating with an exposure, or you can etch this into a material, that you're trying to use. And so if you don't have the degree of flexibility of coating materials and so forth that you have for some exotic material, you might think about making a grating in that material, and that has you can see here too, right? So if you have a field that has a vector in this direction, so it's cutting through these rises here, that's going to see one refractive index. If you cut through it in the other way, say along the fringes, that's going to see another efficiency and another index. And so you can create things like retardation plates, for instance, as well in a material like this. And one of my students had looked at that, again, a number of years ago for making polarization control elements in materials that did not lend themselves to traditional types of coatings for retardation plates and polarizers and things of that sort. So again, so it opened, there's a whole new degree of capability. Now, what if you don't want selectivity? What if you want to make it equal? Well, you can control that to some degree as well through all right, so this has a kind of a material characteristic. So this was 11 microns thick, and by controlling the exposure, again, in this case, we were able to get the P-polarized light and the S-polarized light to kind of cross over at a angle that we wanted to reconstruct it at with equal efficiency. The efficiency is somewhat lower than the peak, but they're equal. And so one of the applications for this that we were looking at was in a wavelength division multiplexer. And so in that case, you have light propagating through a fiber, and its polarization is all over the place, right? When it goes through the fiber, it's mixed up, and there's thermal effects and things like this. So when it gets to that sort of wavelength selective element, you don't know what it is. So if you designed it for S or designed it for P, it's not going to perform as well as you think. And I didn't bring the slide of that, but I had a slide where we looked at the bit error rate for a communication channel, and that bit error rate, really went to nothing, or increased, I should say. The bit error rate increased, the eye diagram closed, and if we designed it in this way, you could see that it really opened up, the eye opened up, and you had a very good signal capability in filtering that. So again, there's a lot of things you have to pay attention to with polarization as well. Some applications require non-polarized operation, so you have to kind of maybe sacrifice a little efficiency to get a good performance for that element. Okay, so that's pretty much the end of the coupled wave analysis that I wanted to go through. The next topic I want to look at is what you're doing in your lab today and yesterday, and that's on multiplex gratings. So again, multiplexing is a really big advantage of holography because you can record, in the same location, the same material, many different elements. So you have basically a store of information there. And we're going to expand on that when we talk about the data storage application. All right, so there's there's two ways you might think of recording a multiplexed hologram. So here, let's say we have a reference beam out here, E sub r, and then we have a bunch of signal beams. Like so. So we may already want to record a large number of these, and in data storage, that's the name of the game. And so here we have, say, E1, E2, all the way down to say E sub m that we're trying to record in that medium. All right. So there's kind of two different ways we can do that. The first way is to illuminate everything with a single exposure, or illuminate the material with a single exposure. With all the signal beams at the same time. I apologize, I was trying to load this up on D2L, but for some reason my connection to D2L was not doing it. So I'll work on that and get it up this afternoon or tomorrow at the latest, but to update, to give you the latest notes on this. But at any rate, so we have one way is to do this single exposure. The other way is to do a sequential exposure where we have one signal beam, so we have one EI plus ER, and then we do another one, and so forth. So we do a sequential exposure where we have individual signal beams with a separate reference beam each time. Okay, so one time we have all the signal beams coming in with one stronger reference beam, and the other time we have weaker reference beams with individual signal beams. Okay. All right. So is there a benefit to doing one over the other? All right. Well, I think I mentioned this before, that if we do a single exposure or a simultaneous exposure with all of these different signal beams and the reference beam, then we're going to end up getting these intermodulation gratings that are formed by each of these signal beams interfering with themselves, right? They're about the same amplitude. If you expose everything at the same time, there's going to be interference between these two beams. There's also going to be interference between this beam, and so forth, okay? So there's going to be a lot of these gratings that are formed between those different signal beams, in addition to the one that you want, which is this one with that one and this one with that one, all right? But you're not really controlling that. You're kind of hitting it with everything at the same time. For the sequential case, there you have, say, this exposure beam with this signal beam. You may have a different exposure beam at a slightly different angle because you may want to reconstruct it separately, not all with the same reference direction. But there, you can think that we have this dynamic range of the material, right? So here's, say, the exposure and the efficiency. You're going to get, again, we have only a limited response of that material to the overall exposure, all right? So there's going to be a limit to the sequential case as well, mainly from the dynamic range of the material. But are there some other issues or other differences in between these? And it turns out that there is. There was an interesting paper written many years ago on this by, here's a copy of the paper, by Lamacchia and Vinciletti. And they show in this paper, and I'll go through the derivation now, that there is a difference between these, which is a little bit more fundamental, all right? So let's look at that. All right, so first let's take the single exposure case. And so what does that look like? Well, that looks like so we'll call this I sub s for single. And here we have a reference beam, we'll call it E sub r bar, plus all of our signal beams. And that's, so we have I equals 1 to m E sub I quantity squared, all right? So what happens when we, in the past we've only done E sub r and E sub o, okay, but now we have a whole bunch of potential E sub o's, all right? And so if we expand this, now we have that I sub s is equal to E sub r bar squared, the reference beam intensity, basically, as we did before, right? And then we also have the summation now of E sub I squared from I equals 1 to m. So we have now the intensity of all the object waves, right? So all of this is going to give us a bias here, because that's just an intensity without any modulation. But the other terms that we get are the the interference terms. All right, so here we have I equals 1 to m, and we have E sub r times E sub I star plus E sub r bar star times E sub I. All right, so that's kind of similar, but we also get these cross terms. So we also have that set of terms, which is a double summation with from k equals 1 to m and j equals 1 to m, but these j and k are not equal, okay, right, because they're two different signal beams. And so here we have E sub j star E sub k plus E sub j E sub k star. So these are the cross terms that I mentioned where these two guys are interfering here, okay? All right, this is what we want, okay? This is the object or the signal waves, signal beam interference. Interference, yeah, sorry, with E sub r. Okay, so there's a lot of terms floating around there. So let's kind of get rid of some of them. Okay, the way you can get rid of them is you can make E sub r. What's normally done, even with display holography, is a lot. Is that normally you want to make your E sub r greater and sometimes significantly greater than E sub I. So since each of those, since our whole object beam consists of lots of E sub i's, we can make E sub r bar much greater than this E sub I, and that in turn is going to mean that this magnitude that we have, e sub r squared, is much greater than e sub I squared. Okay. Now, the result of that is that we have I sub s now is approximately equal to e sub r bar squared, which is our bias. We kind of discount, we're going to say that it's big enough so that even though you're summing m of these, it's still going to be less than e sub r for the bias. And then we have this term here is going to drop out, all right, fortunately. And that's because that's kind of messy. And then we have summation from I equals 1 to m of e sub r I star, e sub r bar, e sub I star plus e sub r bar star, e sub I. Okay, so this is for the single exposure with this particular assumption that the reference beam is much stronger than the individual object beams. Okay? All right, so now, and by the way, this is useful to know when you're, constructing a hologram, what the interference is for that construction. So again, you can model it with, if we're doing this single exposure with a reference beam, this is a coherent addition of a reference beam with lots of object beams, okay? All right, now let's look at the multiple exposure or the let's call it multiple so we don't have the same subscript. Multiple exposure case, aka sequential. And in that case, so here we have I sub m for multiple, and then we have summation from I equals 1 to m, and that's now the coherent summation is of e sub r plus e sub I times e sub r plus e sub I star, okay? So it's different, okay? And e sub r here is not equal, e sub r is not equal to e sub r bar, okay? We will see where the equivalence is, but right now it's not. All right, so when we expand this, so now we have I sub m is equal to m, all right, times e sub r squared plus summation of e sub I squared, I equals 1 to m, and then plus the e sub r, e sub I star plus e sub r star, e sub I, and this is from I equals 1 to m. So here we're not throwing that away because we said that e sub I is about equal to e sub r. All right. Now, we want to compare these two results. This result for the multiple and that result for the single. So we have to do a couple of things. So we'll say, for instance, like the exposure time is the same for the two. So we have the same exposure time. And the other thing that we want to have the same is the bias, okay? And so for that, we can say that we can actually find an equivalent here. And so we'll say that the e sub r bar squared is equal to m times e sub r squared, okay? Or, we have that e sub r bar is equal to m 1/2 number of exposures times e sub r. All right? Yeah, sorry. I'm not paying attention. Okay. All right, so now how can we compare these? Well, let's think about some things that we learned earlier. All right, so remember that if we look at the diffraction efficiency for a single, or let's not use single, for the ith grating, in one of these cases, we can say that the efficiency is proportional to the visibility squared. Remember, we derived that because we said that the efficiency basically is equal to a constant times the exposure time times the visibility squared. We went through and derived that a couple lectures back. And the visibility, which is, again, the fringe visibility that we have, VI, this is equal to Imax minus Imin over Imax plus Imin for that interference pattern that we have. Okay, so if we had, we've done this a few times, if we have two waves, so if we have just, for two beams, all right, there we have that, again, so we have I is equal to I1 plus I2 plus 2 square root of I1, I2 times the cosine of the angle between the two fields, all right? And in that case, the visibility, V, for two beams was equal to 4 times square root of I1, I2 over I1 plus I2 plus 2 square root of I1, I2, and then plus I1 plus I2 minus 2 square root of I1, I2. Or all of that was equal to 2 square root of I1, I2 over I1 plus I2. All right? So so now we can say that if we had a single exposure, right, we have two beams, all right? And so here we have then the visibility of one of these individual gratings that we have is just going to be equal to 2 times the square root of I sub r, right? Because we're talking about the single object beam with the reference beam that we have, over, now the bias has all of the terms in it, right? So here we have summation from I equals 1 to m of I sub I plus I sub r, okay? So again, this was for the single exposure case. All right? Okay, all right, so if we have now, all right, so we talked about beam ratio. So if we have a different beam ratio, so we have I sub r, the reference beam is equal to, here's the beam ratio times I sub I. So we can rewrite this visibility equation for this single or simultaneous exposure case as being equal to V sub I is equal to 2 square root of I sub I times I sub r, which is really equal to beam ratio times I sub I, over summation I equals 1 to m of I sub I plus r times I sub I. All right? So this then equals 2 times the square root of r over m, the number of signal beams or object beams, plus r, right? Because we can like factor out I, or we can cancel I sub I from the top and the bottom of that. So it's independent. So this tells us what the visibility is. It's dictated by the beam ratio that we have, and it's dictated by the number of object beams that we have. All right? So what is the best visibility, or what is the condition, when do we get the maximum visibility? All right? Well, we can take the derivative of V sub I with respect to the beam ratio. We can control the beam ratio if we have a fixed number of object beams in our situation. And when we do that, so we take the derivative of that, set it equal to 0, like you always do trying to find a maximum or minimum. When you do that, we find that you get the maximum v sub I when r is equal to m. Okay? So when you make the beam ratio equal to the number of gratings that you have, you end up with a maximum. It kind of makes sense. When you have that, you have equal object beam intensity and equal reference beam intensity, right? So and we found that, from just 2 beams, that gives us kind of the maximum case too. So, all right. So now, we have this optimum case, and so let's now compare again this single exposure case with the multiple exposure case or the sequential case. So now let's see. So for the single exposure case, all right, we have the visibility V sub I, and we'll put a S out here. This is equal to 2, and we want to compare it to the multiple case. So we'll substitute in this equivalence that we have here, all right?
Sorry, did you say that are we still dealing with the single exposure, or was the first one the sequential?
This is for, this was just in general for 2 beams, okay? And now, and this is, so we found this very general result that, this is the case when we have a 2-beam exposure to get the maximum visibility, which in turn gives us maximum efficiency. So now we're going to look at the single exposure case, utilize the equivalent reference beam intensity, right? We saw here that the two are, we can make the reference beam intensities equal using this relationship, right? Because we want to compare it with the same kind of condition. Does that answer your question okay? Or?
Let's just think about single exposure on that one.
This single exposure, oh, I'm sorry. Oh, here.
Yeah.
All right. So, okay, so let's just take that off. Okay. So that's just like we have 2 beams being, actually, that, this is the situation that we have. This is the single beam exposure case, actually, right? And so I guess I do want to keep that in there. I'm sorry.
But it's for sequential.
But we're only looking at one of the gratings in that simultaneous exposure. The visibility of one of those gratings that are formed in that simultaneous exposure.
Okay, but we're not talking about the single exposure, what we call the single exposure creation.
Okay. All right. So let me see if I could explain this a little bit, a little more clearly. Sorry. So we have the simultaneous case, right? And so if we look at this case and look at the visibility formed by the reference beam and one of those beams, okay, that's what we have here, right? You see, we have one of the object beams, but we have all of those other object beams are going to bias the hologram. Yeah.
So should that be a different index, just to not get the two confused, because you're looking at a single I, but then you're summing over all I.
I don't.
You said it's the bias over all the beam intensities, but you're looking at a single beam, but they're the same index. So V sub I equals, that I is fixed, right?
Okay. Well, yeah. So this is actually for single beam, right? Yeah. That, I guess maybe I should
So it's like, yeah.
make that. Okay. Sorry. So if we, so all I'm going to do now is to write this in terms of the substitute in E sub r bar equals m 1/2 E sub r. So what this does is kind of make the two reference beam fields equal. All right. So let's do that. So we have 2 times m to the 1/2 times E sub r times E sub I over m times E sub r squared plus the summation I equals 1 to m of E sub I squared. So I kind of wrote out, the intensities in terms of the fields. So that's for the single exposure case, all right? And now for the multiple exposure case, what do we have there? Well, here we have a visibility. We'll put an M out there for multiple exposure case. And this is just equal to 2 times E sub r E sub I over m times E sub r squared plus the summation from I equals 1 to m of times E sub I squared. Okay? So this looks, very similar to this, except for this factor of m to the 1/2, right? So this is actually equal to 1 over m to the 1/2 times the visibility for the simultaneous or single shot exposure, okay? And since the efficiency, eta is proportional to the visibility squared, right? We can write the ratio of these two efficiencies, I sub s over eta I sub m, as equal to v sub I s squared over v sub m I squared, and that's equal to m. So we end up with this result that the efficiency for the single exposure case is equal to m times the efficiency for the multiple exposure case. And the reason for that is you're using up that dynamic range for that material a lot faster for that sequential case. You're needing to add this additional, or add a reference beam for each shot versus doing it with the single shot. So you can actually get and this is kind of an interesting fundamental result, that you can get this higher efficiency, however you pay for it with those intermodulation gratings, which detract from it to some degree. Okay, so now so one of the big uses, or projected uses for multiplexing or gratings, is for kind of optical or holographic data storage. And so a holographic data storage system is kind of interesting, and it's been pursued for a number of years now, because of the fact that what you're doing is you're recording data in parallel rather than in a bitwise pattern or a bitwise sequence of, like you store a sequence of bits and then you retrieve those bits. All right. So this, presumably has advantage, because if you can reconstruct that, you get all of the bits at the same time coming out of the system. And if you can possibly use that for display purposes or some other application, it could have great advantage. Back in 1963, there was a kind of a classic paper in applied optics by Van Herdeen, who looked at kind of the storage capabilities of volume holographic materials and concluded or derived that you can basically store, the storage density limit is something like the volume that you have divided by the volume that would be occupied by the wavelength, or lambda cubed. And this, in a 1 centimeter cubed, this has a huge amount of storage capacity associated with it. Okay. However, there's a lot. No one's ever been able to achieve that sort of density for a number of reasons. And so I want to kind of look at a couple of these reasons. So let's think about what we have to do with a data storage system. All right, so in particular, so we're looking at the holographic data storage. And so first off, we have to generate the data. All right, and then we have to do the recording, record the data. And then we have the readout. All right, and so here, this data recording, this is where the multiplexing comes in. It's going to play a big part, because how we can do that multiplexing and how efficient that is going to really determine a lot of what we can achieve. Okay, and the data generation that we have can be done with like a spatial light modulator. When this all first started, people were just using transparencies, but you need to have a dynamic electronic interface. And so the spatial light modulator is a good way to do that. And then the readout is kind of a complement or a complementary process to the multiplexing. All right. And then finally, there's a kind of we're doing the readout, and there's a data transfer step that goes on. And the data transfer, we have to do things like you have to have adequate bit detection. And so that might require some error correction codes in order to correct for data like we were talking about, this eye diagram. You can have these two-dimensional eye diagram kind of equivalents. And then, once you do that, then you can utilize that information that comes out of the system. Okay, and then there's a number of system issues that are involved. One is, for instance, how long does it take to write a hologram, write time? How long is that? That's going to, of course, depend on the recording material and, say, the laser power that you're using and wavelength and things like that. So there's a lot of the material issues now come into play. Naturally, you want this to be very fast. There's another important thing is the data access time. If you have, say, a block of material with data stored in it, how the heck do you access that information? If you send beams through that material, you're going through other areas that were exposed and have other recordings on them. So how do you selectively get to these different parts in the say if you're using like a photorefractive crystal or something like this? So it's not a trivial problem. And then there's the data transfer time. Is another system issue. And this has to do mainly with the detection process, and then any sort of conditioning, data conditioning that you need to do before it's ready for use in the end output. Okay. All right. So those are some of the issues. There's again, just quickly looking at some of these steps here. So in the recording step, one sort of kind of pictorial of that would be here we have a spatial light modulator sending, say, laser light through it to illuminate the various pixels in the modulator. And then, you send in your information in the form of bitmaps that go into this spatial light modulator. That produces an object field, much like we just described, where you have a sort of a simultaneous exposure. So each of these little openings and so forth is going to give you a different object point that's now being recorded in this medium, and you have a particular reference beam, but you also want to retrieve that information at some point, right? So you need to multiplex it with, say, different recording beam parameters. It could be angle. Angle's probably the easiest one that you can do. It's like the one you did in the lab. But there's some others, and I'll show you some of the others here shortly. And so, so the object field that you're recording looks something like this, and all of that information is now going to be stored at the same time. So again, instead of writing each of these bits out serially, we're actually going to take this whole block of information, like a megapixel here or something like 1024 by 1024 bits, and store it as a single field, and then retrieve it, okay, and project that onto a CCD camera, okay. So here just shows the retrieval process. So you come in with a matched reference or reconstruction beam condition, and you illuminate your recording medium, and then that projects this bitmap onto a detector array, and you need the optics to do that correctly and good registration. And then you kind of sequence through different angles or different wavelengths or different shifts and so forth in order to retrieve that information. And so this actually, here's some, this stuff came out of this book that I did a chapter in here, but it's a pretty good book on holographic data storage. But this shows kind of a, one of these bitmaps, and then this shows these bit error rates that you're getting here for the ones and the zeros. So these show the distributions in the zeros and the ones. So you can see here that you get a lot lower here a distribution for the ones because of a lot of additional interference effects that you're getting as opposed to the zeros. So you have to do some error correction codings for this. The bit error rates are rather high, actually. If you think of communication bit error rates or taking a fiber optics class, you might remember that your bit error rates there are like 10 to the minus 12. So the error rates here are higher, but this rates of error correction and data manipulation that you need are much slower for a storage system than it is for a communication system where you're trying to send signals at 10 gigabit through that system. So here, even though you have higher bit rate or higher bit error rates, you're still able to compensate for that with error correction codes. So just as a point of reference, so I worked for a number of years on a project with Hans Kufal and Glenn Sincerbox, and Dimitri Saltis, who co-edited that book. And so we started out that project looking at photorefractive crystals, and we were going to use this fancy angular and wavelength selectivity to go in and do all this. However, the problem of access was a killer, okay? And so what we ended up doing was using a photopolymer, which was a write once, read many photopolymer, and store it on a disk, okay? Now, as soon as you go to a disk, you have a huge technology base to work from. I mean, your CCD players and DVDs and all those, they're all disk-based systems. So they have that whole technology nailed down really well. So rather than develop a whole new accessing method, we went with this method, and it proved to be quite, quite good, and allowed us to demonstrate, very high bit rate capacities and so forth, going to so there's a lot of things that go on in a project. You have all these lofty ideas you're going to try to do it one way, but keep current with what's going on in the rest of the world. So it's kind of an interesting experience to see. So so one of the disadvantages, though, of this is that we went with a photopolymer that was right once. All right, so a lot of times you want to do read and write, and that was the reason that motivated us for the photorefractive crystal in the initial stage, because you could actually erase that material and then rewrite it. However, it was slow, so there wasn't that much of an advantage. It was better just to store lots of information and then have the ability to retrieve where that information was pretty quickly. That was a huge advantage in the development of that particular system. Okay, so next time I'm going to talk about, well, maybe I have 2 minutes. That's a lot of time, I guess. I can finish up one other thing. So let's talk a little bit about the storage capacity or storage density. All right. So if we are talking about the capacity of a memory, so the storage what do we really mean? And so this might be capacity or density. So basically, that storage density, say, is equal to the total amount of information in the memory. Total info in the memory divided by the area occupied by that. Right? Okay, so if we have a hologram that is recorded and on the surface, all right, so here again, so if we have, again, some of the configurations that we'll see are useful for this, and we talked about this before, is the Fourier transform. So here we have basically a spot. This is the SLM. And so this is the hologram here, and then we have, say, a reference beam coming in off the side to record that. So if we think about the storage density for a single surface hologram, that's going to be equal to, say, a two-dimensional holographic storage is just equal to the number of bits over the number of microns that storage of those bits take up. Okay? Now, and so let's call this for the hologram, all right? Now, if we have a CD player, a CD player also has a kind of a storage density, but its density is for a single axial bit. Here in the holographic storage, we have a system where we actually have a kind of some off-axis imagery going on, although it's close to the axis. And so that tends to degrade the overall the image, right, or the density, or it spreads it out, basically. We're spreading out those bits over a much larger area. So if we were to compare, say, the two-dimensional storage density of the hologram to the two-dimensional density of a CD player, this is going to be actually less than 1 because of these because of the difference between just recording a point, which you can do at much higher resolution, versus a distributed, set of spatial frequencies. Okay, so why do it? Why do the holography? Well, the advantage of the holography again is the multiplexing. All right, and so we now have this three-dimensional holographic density capability, which is going to be equal to m times this two-dimensional holographic storage density. And that product is, so m alpha now is going to be much, much greater than 1, which means that this three-dimensional storage capacity can be much, much greater than the density that you have for the CD. Okay. So again, this multiplexing is very critical in order to achieve very high storage densities that you would need in order to justify the holographic store. Okay, so I'm going to cover a few more topics on the data storage next time, and then start on computer-generated holography. So, okay, so see you on Thursday.